Welcome back everyone. This is the last week of the course. We will cover some good practice in security design and emerging hardware security topics. We will talk about the Trust Platform Module, or TPM, with focus on its crypto key generation and management structure. Then we will learn the basic concepts of physical unclonable function. We will discuss the vulnerabilities, attacks, and countermeasures in FPGA design and FPGA-based systems. We will conclude the week and the course with a brief overview of the role that hardware plays in security and trust. We will need some basic knowledge of digital logic design to understand the physical unclonable function. A review on physical attacks, IP protections, and hardware Trojan will be helpful for the materials related to FPGA system security. Trust Platform Module, or TPM in short, refers to both the set of specifications for a secure crypto processor and the implementation of these specifications on a chip. We will focus our discussion on the TPS chips. The specifications can be found in the web page of the Trusted Computing Group. TPM chips can be installed on the motherboard and is used in almost all of the PCs, laptops, and smartphones. It is suggested to use TPM together with firewalls, antivirus software, smart card, and biometric verification. Many companies are making their own TPM chips. A TPM chip's main function include secure generation of cryptographic keys, protection of these keys, generating pseudo-random numbers, hardware authentication, sealed storage of password, keys, and digital certificates, and remote attestation. Remote attestation allows changes to the user's computer to be detected by authorized parties. TPM has many types of keys. Among them, the endorsement key is perhaps the most important one. This is a RSA public-private key pair. It is created only once during the lifetime of the TPM. Normally, it is generated by the TPM manufacturer after the TPM chip is fabricated and tested. The private key is stored inside the TPM and can be used internally for decryption. It will never be reviewed or accessed outside the TPM. The storage root key, or SRK, is another important key stored inside the TPM. It is created when the TPM's ownership is created. The TPM's endorsement key and a user-specified password will be used to generate the SRK. The attestation identify key, or AIK, is another RSA key pair designed for attestation. The public key will be signed by the endorsement key. Then it will be sent to a trusted certificate authority, or known as CA. The CA will validate the endorsement key and issue a certificate for the attestation identity key. TPM will authenticate itself using this certificate. This is the start of the direct anonymous attestation. Storage keys are asymmetric keys used for encrypting data or other keys. This encryption process is sometimes referred to as wrapping. Signing keys are general-purpose keys used to sign applications data or messages. Binder keys are used to encrypt a small amount of data or key on one platform and decrypt it on another platform. Authentication keys are symmetric keys used to protect transport sessions involving the TPM. Legacy keys are keys which can be exported to another TPM after creation and may be used for signing and encryption operations. They are referenced to specific users and their application fields. Based on whether a key can be transferred from one TPM to another, the TPM keys will have one of the following attributes. The non-migratable keys, or NMK, are those created for one TPM and cannot be migrated or exported to another TPM. They are stored in TPM's shielded locations, and the TPM can create certificate for non-migratable keys. Migratable keys, or MK, are the keys that are not generated for a specific TPM. They can be generated either inside or outside a TPM. They can be integrated inside a TPM or moved from one TPM to another one. Migratable keys are only trusted by the party who generate them. Certified migratable keys, or CMK, are generated inside a TPM like non-migratable keys, but they can be migrated to another TPM. At the time when they are created, the creator has to pick up a migration authority, or MA, or migration selection authority, or MSA, which will have the authority to migrate the key. CMKs can both be migrated and also be considered secure as long as the MSA and the MAs to migrate the keys are trusted. Here are some advantages and disadvantages of using TPM. Using TPM, it will add security against the physical threat and attacks. It can also give user convenience with the single sign-on feature. However, there are also a couple of concerns of using TPM. First, the biggest concern is about the user privacy. With all the user data stored on TPM, once the TPM is compromised, users' sensitive data will be lost. And second, as we have mentioned, there are many TPM vendors. How can we trust this hardware design process, and how can we trust these vendors? That is another concern. So here there are some useful links about the TPM. We give the homepage of the Trust Computing Group and how to use TPM with Linux and the TPM and the BitLocker in Windows 8 operating system. Finally, besides TPM, there are many good secure design practices from most of the leading companies such as ARM, Cisco, HP, IBM, Intel, as well as the major FPGA vendors such as Altera and Xilinx. I'm not going to do commercial for any of them. If you are interested, you can easily find them from their webpage on how they can do secure system design.